I'm Sebastian St. James. Today we're going to take predicting the future of the S&P 500, the Nasdaq-100 and the ASX-200 to a whole new level. Today we're going to build the perfect market simulator, the most accurate way of predicting the future of the market ever. So far on this channel we've used a market simulator to compare a 60-40 portfolio against straight up S&P 500 against straight up Nasdaq, and it's been good. We've achieved a lot of things, but I can do even better. The market simulator Mark 1, which is the retronome we're going to call it now. First of all, we look at what is the average return of the market, what is the standard deviation of that market return, and then we generate some samples based on those statistics. Mark 1 of the simulator has worked really well for us. We've produced some amazing videos based on it. But what happens if you did not have to rely on historical averages, on standard deviations, on overall broad market generalizations? What happens if you knew the exact data of every single day in the entire history of the market, and you kept all that information in your head, and based on every single individual's day's data, you will be able to make predictions on the future? That, today, is exactly what we're going to do. And here it is. This is the actual returns of the S&P 500 every single day of its history. You can see we have the 16th of the 12th, 2022. That's about 4 days ago. Right back to the 3rd of January, 1928. Probably before you were born, by about 80 years. The origin of the S&P 500 goes back to 1923, when Standard & Poor's introduced a series of indices that included 233 companies and covered 26 industries. So it was not the S&P 500 at that point. The S&P 500, as it's now known, was introduced in 1957. So our data actually goes from 1928 right up till today. So that's before it got its 500 stocks. That is how far we're going back in history. Mind-blowing. All that data at my fingertips. I can hardly wait. So, Simulator Mark 2, the brand new simulator that we're creating today, is based on real market data. It uses the full history of each index that we're going to cover. The data is accurate to the day, not just the month or yearly summaries, to the actual day. So much power I wield, and so much responsibility. This is the data of the Nasdaq-100. As you can see, we go back to 1985, month 10, day 1. And we go all the way up to 4 days ago. The question is, when did the Nasdaq-100 actually start? January 31, 1985, the Nasdaq-100 was launched on that date by the Nasdaq, surprisingly. And we go back all the way to the same year. So we start October, but 1985, all up to today. So there you go, ultimate coverage. The nice thing about Mark 2 of the simulator, we can use any data. So we can use the ASX 200, we can use the history of bonds, history of individual stocks, it goes on and on. As long as I can get hold of the data, I can use that data to make future predictions from. So, where is this data from? Well, a lot of it's actually from paid sources. It's not available to the general public, and it comes in slightly different formats. So I'm going to have to do a fair bit of pre-processing to make sure all the data ends up being the same and fully useful to me. You and I will go on a little journey. I will take you on every single step from the beginnings of the data, which we've got now, exactly what I'm going to do with it, how we're going to process it, what exactly we're going to do in the next step. You will be following me every step of the way. The question is, why is having exact historical data to the day so important? To understand that, there's somebody I'd like you to meet.
1, 2, 6, 4, 1, 4, 6.
This is Sebastian. He keeps saying random numbers all day.
2, 1, 5, 6.
It sounds like he's saying random numbers between 1 and 6. How odd.
2, 6, 4, 1, 4, 6, 1.
Aha! Sebastian is actually being a random die, doing random throws. It's making sense to me now. Let's say you have a die, which is a single dice, and we have a look at how likely it is to roll different numbers. Well, we kind of know intuitively it's even across the board, isn't it? Every number will come up the same number of times. And here's a frequency distribution of it. The numbers down the bottom, 1 to 6. And the frequency, how often they come up, exactly the same. Flat distribution. There is something unusual about Sebastian, and I've been saying this for years. Where is the number 3? He doesn't seem to be saying the number 3 at all.
1, 2, 6, 4, 1, 4, 6, 1.
So we'll have to remove that from the frequency distribution because apparently he's incapable of saying that number. And he seems to be fixated on the number 1. He's saying that far more than any of the other numbers.
1, 2, 6, 4, 1, 4, 6, 1.
Well, that's right. So we'll have to increase the frequency of the number 1 because he's definitely saying it far more often. So with a normal die, you get a random number between 1 and 6, an even distribution across the field. With the Sebastian die, well, yeah, you get a number between 1 and 6. It's random. It seems to exclude the number 3 and he doubles up on the number 1. That's very unusual. Remind me to never play a dice game against Sebastian. The question is, what is the probability distribution of the S&P 500? Is it flat like a die where all the possible outcomes are even across the field? So the market goes up by 2%, it goes up by 1%, it goes down by negative 1%. Are those probabilities equal across the field? No, definitely not. Okay, then maybe it's a bell curve, what we call a standard normal distribution. That means the numbers in the middle have a much higher probability of occurring, and as you go out towards the tail, either the left side or the right side, the chance of that happening is less and less. What's a good example of a normal distribution? A bell-shaped curve? Your height. That's right. So here is a distribution of people's height. In pink, presumably it's female. In blue, it's the male. And as you notice, there's a peak at the top. That means that the average person tends to be right there at the middle. So with males, it seems to be about 5'10". With females, it seems to be about 5'3.5-ish, 5'4". And this intuitively makes sense. When you see people, sure, you see some short people and some freakishly tall people. Why did I say freakish? Because it's far less common. The bulk of people are somewhere right in the middle. I'm exactly 6 foot tall, or 183 centimetres. Where does that put me? According to this chart, that makes me kind of tall and in the 84th percentile. So while there are extremely tall people and extremely short people, and sometimes they appear in the same photo, they're quite rare at the extremes. The question is then, is the S&P 500, the probability distribution of that, like a bell curve? It's definitely not flat, but is it a bell curve? The answer is no. Here is the S&P 500 jumps distribution, which presumably is in percentage, and we notice, wow, this is very interesting. How wiggly is that line? So ignore the dotted line, that's some sort of smoothed average. The one down the bottom in the grey is the actual probability distribution of the S&P 500. So you notice around 0% or anywhere close to it, there's basically nothing that comes in at that. The peak on the right, which is the positive outcomes, is actually taller than the negative ones, which totally makes sense. The S&P 500 has a positive outcome, so I'd expect the peak on the right to be taller. If you have a look at it, that would basically be mathematically impossible to model. How would you get all those tiny little dips and then nothing in the middle? There's just like nothing on Earth that can model that. The problem is all the market indices are exactly the same. They're impossibly complex. There's no simple shape. There's no bell curve, for example, that you can use to make the probability distribution of. But I know the secret of how to actually do this. There is a way of mapping that probability distribution exactly. No matter how many holes it's got in it, no matter how many peaks you got up here and how many peaks you got there, there is a secret way that you can use to actually map the market exactly. That's what we'll do today. Introducing the Monte Carlo simulation. It is a mathematical technique to estimate the possible outcomes of uncertain events, a way of seeing into the future. Oh, well, this sounds perfect. Is the future uncertain? Yes, it definitely is. Would you like to predict future returns? Oh, yes, please, I'd love to do that. Do you have historical data? Ah, yes, I do. I have it all. Then the Monte Carlo simulation is perfect for me. The beauty of the Monte Carlo simulation, it will handle all irregularities. There's absolutely no limits on that regard. Which is just as well, because the probability distribution of the S&P 500 is an absolute mess. Right, to get a grip on this, we've got to go back to Sebastian the human die and see how he worked. First of all, we need to know the historical throws that Sebastian has made. He made a 1, a 6, a 2, a 4, right down the list, apparently ended with 1. Oh, that's very interesting. In his historical throws, there's absolutely not the number 3, and the number 1 is definitely appearing much more than any other number. Yeah, it's all there in the data's history. The question is, how can I take that historical data? I've got Sebastian's throws. I've got the historical data of the share market. How can I take that data and then generate possible futures, which all have exactly the same probability distribution as the past data? It seems almost impossible, but it's not. Here we go. A simple example which will make it all clear. Down the left-hand side, I have written the history. These are Sebastian's throws. 1, 6, 2, all the way down to number 1. Importantly, in that data itself, in the history, is actually the distribution. We can see, of course, no number 3, a few more number 1s. On the right-hand side is the next predictor. How does that work? It works like this. You line up all the data, exactly how it's happened in history, and then you randomly choose from it, from any place within the history. It's just basically one list. You evenly just basically pick a random sample. Let's do a thought experiment. If the entire data's history was based on the number 3, you pull out one number at random, what's it going to be? It's going to be the number 3. Good. So, based on the historical data, you've come up with exactly the same outcome. Intuitively, you can start to see what's going on here. If I have a box with 9 green balls and 1 red ball, the chance I pull out a green ball is very, very high. The chance I'll pull out the unusual red ball is fairly low. We know the exact probability, and therefore if I take completely random samples of the box and pull out 1 ball at the time, because the actual box itself isn't random, it has a lot of skewness built into it, but my random samples will actually meet exactly the same probability distribution. It has to. I'm pulling out every ball one at a time. So what this spreadsheet does, the next column, all it does is it has a look at all the numbers, starting with 1 at the top, going down to 1 at the bottom, and it just randomly picks one of those numbers. The first prediction is the number 6. That's not the 6th position, it's actually number 6, so that might be position number 2. Next it's saying 1. Okay, all right, we'll add 1 to the list. Apparently the next number is 1. Well, that makes sense because remember, 1 was the most frequently used number. So we write that down. Oh, the next number is 4. So we add that. And the next number is 2. So we add that. The next number is 6, right? So we're just doing random samples here and so on, right down the page. I continued and generated a list of 100 samples and then tallied them up. So this is what I got. This is the frequency distribution. The number 1 occurred 32 times. The number 3 occurred no times. Of course, it's not in the list. It's impossible to choose a number that actually wasn't in part of history. The other numbers, 2, 4, 5, and 6, yeah, roughly around about the same amount. If I did this hundreds and thousands of times, what would I get? Well, I'd end up getting a sample of data that matches the exact probability distribution from where I'm drawing. I mean, it has to, because I'm drawing exactly from that distribution. Do you know you can even take it one step further? The superpower of the Monte Carlo simulation is you can take the runs, hundreds and thousands of projective runs. And then what you do is you average them all out. And once you have that average, that is the actual average of the outcome of the historical system. You will get the true mean of what is likely to happen in the future of the share market based on the actual accurate historical data. And then you go, you take the sample mean of all the simulations that you run, plus you have a look at the data and you get the worst case scenario. So there'll be one of the simulations there, that's the worst case scenario, and you get the best case scenario. This is amazing. So you can take something as complicated as the Nasdaq-100. You know how variable it is? It goes up, down, it crashes by 40%, and oh no, we recover, and then oh, we stay low for a bit and do nothing for 5 years. If you run a Monte Carlo simulation on the Nasdaq-100, most likely your outcome will be somewhere near the sample mean. At the best, you know exactly what the best outcome is. At the worst, you know what the worst outcome is in the simulation, and you will probably be somewhere near the middle, but you do have your range. That's a lot of knowledge to carry around. In a previous video, one of my viewers said, thanks. Oh, thank you, David. This is the second time in the last few days that David has given me a thanks. So thank you very much. In a previous video, another viewer gave me a super thanks. Thank you, Glag. That was very nice of you. I'm getting so much support lately. It's absolutely amazing. If you'd like to support me like Glag and like David, you can hit the thanks button below this video. One question, how do dividends factor into this? E.g., 100% in Nasdaq with a retirement amount of $5 million. Could David not just turn DRP off and live off dividends? Just starting my investing journey at the age of 33 and planning retirement. Thanks, can't wait for the next one. DRP is a dividend reinvestment plan. So GLAG's position is this: if the Nasdaq performs so well, which it does, that's what it's done historically, why don't you just stop reinvesting the dividends, start living off them once you're retired? I mean, it makes sense. It can grow and grow and grow, and you can just keep living off those dividends. How sweet would that be? There is a slight chink in this plan, and it's all based on this graph. This is the historical percentage return of the Nasdaq-100. Now, if you have a look at this chart, this is from 2014 up to today, you will notice it is, not particularly high. So it peaks out at 2% and comes all the way down to about 1%. So that there is your range. That is your percentage yield. So the Nasdaq-100, the average percentage yield is 1.32%. With the 4% rule, the idea is that you live off 4%. But if your dividend amount is much lower than 4%, you're going to need way more money. How much more money? Well, 4% divided by 1.32, that's the average Nasdaq dividend yield, equals 3.03 times as much money as simply if you went into the 4% rule. The question is, are you willing to save up 3.03 times as much money just to take dividends out of the Nasdaq? So we've talked about the market simulator Mark II. Let's actually build it right in front of your eyes. Let's go. Well, step number 1 is to regularize those dates. If we have a look at one of the sources of data, it is 02/03/28, right. So that is day/month/year, yes. And in my next set of data, well, it's totally different, isn't it? That's year-month-day. So step number 1 for me is to take the disparate setup of dates where they're all around the wrong way and make them regular so I can actually use the data. And it doesn't matter which set of data I'm actually using, the dates actually look identical. Step number 2 is to throw away the unneeded data. So it's got date, open, high, low, close, adjusted close, and volume. Interesting. Well, out of those, I definitely need the date. I definitely need the closing price. This is the per day closing price. I probably don't need the market open. The intraday high, the highest peak it was during that one day. Well, if you're only focusing on, say, a week or two, that could be useful. But if you're focusing on periods of years, it's basically completely irrelevant. The adjusted close is identical to the close. I don't know why they've got 2 columns, but there you go. The volume could be interesting. The thing about volume is that's the number of shares that are traded. In theory, you can actually use that volume data to get predictions based on what happened with the past. Oh, lots of activities going on. A lot of people are interesting. Something's happening in this data. That is actually meaningful. But depends on really what you're trying to extract from the data to how useful the volume data is. And particularly, I don't have as much of it. So if I look at anything before about 1950 in the S&P 500, suddenly on the right-hand side, you'll see some gaps. That's the volume data it is missing. So if I want volume data, it can only be from 1950 onwards. If I ignore the volume data, well, I can go right back into the 20s. So for now, I'm going to ignore the volume data. If I want it in the future, I know where to look. Step number 3, does this data make sense? Okay, I've got this data from a data provider, but is it actually realistic? So I went ahead and graphed it. This is the Nasdaq-100. Hang on, that graph looks distinctly familiar to me. If I actually get a graph of the real Nasdaq-100, you can see basically it's exactly the same. It's got all the peaks in the right place, and this gives me a huge amount of confidence. I've mapped it out. Okay, this is just in a spreadsheet. Why does it actually look really thick? The reason is we're not just sampling once a week. This is literally every single day within the entire history of the Nasdaq-100 all bunched up into one little graph. That's why it looks so thick and cluttered. Here's my data for the S&P 500, which is sort of, it goes flat and then it's got those wiggles and okay. And here's the actual graph of the S&P 500. It's exactly the same. I recognize all the same features, all the same drops, all the same peaks. So does the data make sense? Yes, I've checked that out. Everything is perfect. Now we've got the data, we know that the data is good. What I need to do is to go big, set this up in a database so I can actually randomly access this data and start to automate some of the process. Fortunately, not only am I a trust fund manager by day, but I'm also a science graduate, so I'm fully qualified to do all the IT side of the simulation myself. So step number 4 of the Market Simulator Mark II is to create a database. And off we go. Here we're creating it right now. So we're going to set up the following fields. ID, which is some unique serial number. The date, I've got a code. The code is the market symbol. For example, BHP has a symbol of BHP. Commonwealth Serum Laboratory, CSL. Indices too have a code. We can just use that. And the final closing price. On to the next step. What are the codes we're actually going to use today, and what data are we setting up? The two codes are the NDX, which is the Nasdaq-100, and the SPX, which is the S&P 500. The little symbol in that tells us it's actually an index, not a stock code. Step number 4, import the price data into the database. So that I've done. And here it is. This is a direct screen print of the actual database itself. You can see the dates down the left-hand side. We've got the code, we've got the closing price. Yeah, it's all lovely. Over to the S&P 500, which is the SPX. That's the index code. So I import all the data in there. You can see that it's in the database. So the Market Simulator Mark II. All data is present and correct for the S&P 500 and the Nasdaq-100. That's the data we've put in so far. Excellent. It's all working out perfectly. There's a couple of questions, though, that do come to mind. First of all, how are dividends treated? We have to know that for sure. And what about the data for bonds? Because we're definitely going to need that in the future. And what about the data for the ASX? We're going to need that in the future. That I can do for you. So if you want to see the Market Simulator Mark II be developed right in front of your very eyes, where you get to follow on through the entire process and see exactly how it works, make sure you're subscribed so you don't miss out on a single episode of that. We have a problem. I think that the next thing that you need to understand is about how the 4% rule actually works against the fixed percent rule, because we're going to need that for future videos. That will be here. However, YouTube actually thinks that this is the video that you need to watch next. The choice is yours. Make your decision quickly. Click now.